There we go. All right, so I'm getting the recording started. Um, so what we'll do today is, your lab is going to be the second part of getting familiarized with the components inside the processor. So this time I'll show you what it involves. Okay, so I'll even show you what it's going to involve. This is your lab for today. Today is the 20th. Okay, pretty sure about that. And when I look at the questions, you can see the pictures. So there'll be one question related to a demultiplexer, one question related to the ROM component, and then one more question related to the RAM component. Now, I do remember in this class, I have already talked about the RAM component, how to complete a read cycle, how to complete a write cycle. So, you guys already have, everything that you need to do the lab. So what I'll do today is, during the lecture time, is not to go over, all the stuff that you'll be doing with the lab because you have enough time to do it anyway. So, so what I'll do is I'm actually going to start to talk about the processor itself. Okay, and I'll explain, how it works, in very, very low detail. So I think the recording today is going to be quite helpful. If you just kind of write down the time mark, of certain, major concepts, that might be helpful too, because it will help you to locate those very specific discussions, in the video without having to watch the entire thing over again. Okay, so so the first thing is how do we run the processor? I don't want you guys to run Logisim when I'm doing this because otherwise you'll be busy trying to copy what I do. Everything is being recorded, so you don't have to worry about. But I'm concerned that I may not be able to do that myself. Nope, nope, should not be a concern at all. In that case. All right, so I'm going to go to the share drive. And remember, it's all getting recorded, so you don't have to follow my steps here. Instead, it is more important for you to focus on the concepts and what I talk about. All right, so we go to the processor subfolder. By the time we have any activity to do with the processor, it will give you the actual instructions of where to go, what files to download, and how to get it started. So once again, don't worry about the detail of how to get this thing started. Oh, by the way, there's one funny thing that you might encounter, with a lab computer. For those of you who are using the lab computers in this room, Java is getting uninstalled. Okay, so I already experienced that problem upstairs in room 321. And the reason why Java was uninstalled was because Oracle is trying to charge people for using Java. And they have been doing that according to Oracle for 3 years already. They just never caught ARC in the past. So I'm suspecting every time we start up Java, it sends a little ping to mothership. And the mothership would look up the IP address and go like, which organization does it belong to? Now, if it belongs to like AT&T, customer service and stuff like that, it's not customer service, but belong to a customer of AT&T, it's no big deal. It's an individual use, but if it's coming from Los Rios, they go like, hey, this is an institution. They're using Java, and then they'll look up the paid customer list, and we are not on that list, and that's why they have been kind of trying to get us to pay, a fee for the license.
So you can use Java individually as like one person for free, but you can't use it as a
That's right.
bunch of
Yep.
people.
Yep. And Oracle has been backpedaling a little bit and admit that was not such a great idea. So now they have, according to, from what I can understand, is there are two licenses even for institutions. One is quote unquote free, in which the license says, we are not liable for anything that happens to your computer and your data. And then the other one says, well, this is the best product in terms of security and reliability. It's gonna work. So but that's just my understanding, which can be incorrect.
I feel like they're going to leave the free one a couple security patches behind.
That appears to be the case. I don't think Logisim is going to be a major concern, for security stuff. Yes, somebody might steal your design.
Like for the free version, for security reasons, you aren't allowed to import modules or libraries?
I'm just using OpenJDK, so that comes without any warranty to begin with. So it's like, okay, it doesn't impact me at all. Fine. All right, so there are three files that are needed in order for the processor to work. So these are the three. Once again, you don't have to copy everything that I'm doing right now because in the next lab, you will be given these instructions anyway. And you can always watch the video again if you so want to. So we're going to download these three files. I got all the files downloaded already, but I'm just showing you, what you need to do. So what Google Drive does is it will zip the files into a single zip file, and then you just have to unzip it, on your side, and that's all you need to do. So give you a zip file, save it to whatever location you want to save it, and then just unzip it. So from the perspective of your computer, I'm looking for the command line interface. It is not on the other side. Okay, that's fine. I'll put it on this side here. So from the perspective of the command line interface, um, and I can go straight to I where I have it already installed. So I made a processor subfolder, and I just have all the files here. You can see I have Logisim, I have processor 0004, I have register bank, and I also have ALU dot circuit here. And the way you start it up is, if you're using Windows, you can just double click on you can double click on Logisim, um, and then load processor 0004 from it. If you want to do it from the command line, on the other hand, you can do it in one single command. So you can write a tiny little script to do it, so it's actually even more convenient than using the GUI. So the way I do it is, java-jar, and then you give it the jar file name, and then you give it the processor file name. Press the enter key, and here we have the main processor. So what I want to do is I want to illustrate how we can add the content of two registers. Okay, as an example. Okay, so to add the two registers, the first thing is, what registers are we talking about? There are plenty of registers here. Well, in terms of your software accessible or the ones that you can specify in software, there are only four. They're all living inside this part here, which is called the register bank. So inside the register bank are the four registers. I just call these registers A, B, C, and D, just as a name. So there are four registers here. And the way the register bank works is we have several inputs. Okay, so these are all input pins. So one input pin is register in, which is used to update the content of a register, one at a time. We have a decoder here. A decoder is basically a demultiplexer where there's a constant one as its only input. So it has an implicit 1-bit 1 as its input, and it can basically do the same thing as a demultiplexer, which is basically saying, okay, which one of the outputs is getting that 1? Okay, and it has to be enabled in order for that 1 to go out. So the decoder itself has its own enable pin. This is the enable of the decoder. When this is a 0, all of the outputs of the decoder are zeros as well. So that would make sure that none of the four registers is paying attention to anything. Okay, so that's kind of the quote unquote default state because we don't want the registers to change its content when we don't want it to change the content. And then we have the select for the decoder, which is the same thing as a select for a demultiplexer. In other words, these two bits over here is specifying which output of the decoder is going to get a 1 if and only if the decoder is enabled. So we have output 0, which is 0, 0, output 1, which is 0, 1. We have output 2, which is output 1, 0 in binary. And then we have output 3, which is output 1, 1 in binary. Are we doing okay so far? Because if there are questions at this point, I would like to address those questions as soon as possible. No questions? Okay. So now we take a look at how are these things wired up. So you can see how register in goes into the D port of all four registers. So that's why, earlier I said, as in last week, that's why I said, the enable of a D flip-flop controls who is paying attention. Because you can see the same data is coming in and is fed to the inputs of all four registers. A register is nothing more than a gang of D flip-flops because a single D flip-flop can only remember one bit. So when you have a gang of 8 of them, now we can remember a byte. So that's basically the relationship between what we call a register and what we know as D flip-flop from the discussion from, I think, mostly last week. All right. So the enable, on the other hand, are individual, and they're all coming out of the decoder, which means the decoder is the mechanism to basically say which register should be paying attention. And then we have the clock. The clock is also shared. This is the clock line. And you can see they are all shared. They all go to one particular input pin for the register bank. So from the outside perspective, from the circuit that is outside of the register bank, we just have to feed it the clock signal. On the output side, we have, there's the reset button here. So the reset is also, multi-dropped, which means it is a single node connected to the reset of every single register. So when we want to reset the entire processor, the registers will also have their content reset to 0. So when it comes to the output, it's a little bit more complex, but not by too much. There are two outputs out of the entire register bank. The first one is register output 0, and the second one is register output 1. So potentially, okay, it's entirely up to these two select input pins. So you can basically select any one of these four registers as register output 0, and then you can also select any one of the four registers as output 1. They can be the same register. They can be different registers. You can enable one but disable the other one. Or I should say you can pay attention to one but ignore the other one. Is that okay? So the mechanism to control which register, A, B, C, or D, becomes connected to register output 0 is using a mechanism that is very much like the reverse of a decoder, except this one is a multiplexer. So this way, I can control which input of the multiplexer connects to the output of the multiplexer, and that is controlled by the select bit. So register output 0 select selects which one of the input, which one of the A, B, C, or D register connects to the output, and then the same thing for register output select. Register output 1 select, which selects which one of the registers A, B, C, or D connects to the output of register 1. Excuse me, register output 1. There we go. Is that okay? So this is how we are making use of the most basic um, constructs or devices to make up a larger device. Okay. So what we want to do is I just want to add two numbers. Okay, so I'm going to stick some numbers into these registers just so that we're not adding zeros, 0, 0 to 0, 0, and we can never tell whether it actually happened correctly or not. So I'm going to stick a particular constant into register B. Register B is an 8-bit register, which means we need 2 full hexadecimal digits to specify its content. So I'm going to put a 4B over here. And then the other register I want to add, to register B is going to be register C. I will put like something a little bit simpler, maybe just 0, 2 in here. So I want to add 0, 2 in register C to the 4B in register B. So the end result should be 4, B, C, D, right? 4D. And I want the result to be stored back into register B. So I'm basically giving myself something to do. And now the question is, how do we get it done? Is that okay? So I have set up an objective, and I need to figure out how to get it done now. Are there any questions at this point regarding the register bank, the mechanisms inside the register bank, and what I am about to do, what I would like to do? Yep.
I might have not caught it. What's the ABCD? Like the ones.
They're just names. They're just names of the registers.
No, like the.
The top
Yeah.
output pins?
Upper pins.
Okay, so you're referring to these output pins?
Yeah.
They are really just mirrors of the actual state of each register. It allows me to design a what is known as a logic analyzer, so that we can actually trace the execution of the program and be able to track the changes of the registers as the program executes. So the output pins is only for that purpose. It serves no functional purpose, for what we are trying to do here. But it does enable a tool that will let you debug your program in a much easier way compared to without those things. All right. Good question. Any other questions? All right. So without any other questions, I am going to write down what I am about to do using a text editor. And I may not have one. Oh, I do have one running. Okay, so this is the one that's running. I'm going to open a new window. So I'm going to describe what I want to do. And it is basically using pseudo C syntax, which is register B plus equal to register, what is the other one? Register C in this case. So this is what I want to do. Register B is going to store the result of register B plus register C. Is that okay? Does everybody understand the plus equal operator in C, C++? Okay? All right, so this is what I want to do. The question is, how can I get it done? So now you have to take a step out, and it's a big, huge mess here, but I can tell you there are only a few key components to the entire processor. The rest are only here to support the function, to basically help route, between the components. So the other component that is going to be super useful in this case is the ALU. This is the ALU, which stands for Arithmetic and Logic Unit. This is the one part that is responsible to do all the calculations, addition, subtraction, and comparison. It will do some bitwise operations like and, or, not, and also right shifting. It will give you the result, like, after you do a subtraction, it will tell you whether there's a borrow, the overall borrow. It will tell you whether there's an overflow. It will tell you about the sign bit, and also whether the L flag is a 1 or not. If all of those things are not sounding familiar to you, it is a good time to review binary comparison, because that's when we talked about all the flags. So even though I would not try to make this class, make the exams comprehensive, they are intrinsically comprehensive, because it is not possible to ignore what we have learned in an earlier part of the semester and still be able to complete the exam of the later part. All right, so let's take a look. Let's take a closer look at the ALU here. So right click, and then we go to View ALU. This is the inside of the ALU looks like. So now, we can identify the demultiplexer. DMX stands for demultiplexer. We know kind of what they do, right? The incoming, there's an input here, and then using the select, which is all the way down here, we can now select which output connects to the input. And there's an enable, which means we can basically make the demultiplexer output absolutely nothing to save power in most cases. But we also have some other stuff, like this is an adder, and we see it's an adder because, well, once we click on it, it says it's an adder. This is a subtractor, this is a right shifter, this is a NOT gate, this is an AND gate, this is an OR gate. Did we talk about this in the previous class? We did? Okay. So now that we know which component we want to use, which is the adder, because after all, we want to add the two things. So now the question is, how do I get the content of register B to one of the two inputs here, and then get the content of register C also to the other input of this component? That becomes the next question. Okay? So this type of reasoning is just looking at the dependency. Okay, I'm looking at where the source of the data are, and then I look at the component that can do the calculation. And now the question is, okay, how do I configure all the multiplexers and demultiplexers along the way to make this path happen? Is that okay? All right. So now we do some backtracking. Okay, so we look at this particular wire, and we ask, how do we get this wire to connect to this input pin? Well, it's a demultiplexer, so I need output 0 to connect to the input of this demultiplexer. So how do I get it done? Well, first of all, the enable needs to be a 1. And then second, this particular select needs to be 0, 0. Is that okay? So I know it is extremely tedious, but that is how we figure out, how the processor works. Okay, is to look at each component. We look at what we want to accomplish. We look at what components eventually will get it done, and then we look at how we're going to route the components. We are going to establish the routes between the components. What about the other input? Well, the other input is here. Click on it. And it is the output 0 of another demultiplexer, which connects to another input pin. Well, as it turns out, the enable, they're all connected. So if I enable one demultiplexer, it automatically enables the other demultiplexer. And also, when you look at select, they're also shared, which means if I select output 0 of the first demultiplexer, it will automatically select the output 0 of the second demultiplexer. And that's because they should be all synchronized. So are we good so far? So inside the processor, this is how we decide what operation do we want to do. If I change the select to 0, 0, 1, then I'll be subtracting. If I select 0, 0, 2, it's going to be doing the right shift. If I select it to be 0, let's see, 0, 0, 0, 1, 1, it's going to be a bitwise NOT. If I select 1, 0, 0, it's going to be doing a bitwise AND. And if I select the last one, which is 1, 0, 1, then it will be doing a bitwise OR. Is that okay? So these 3 bits right here, okay, they are really important because they specify what operation do you want to do with the inputs. That's what it's trying to control. The enable is just enable, because if you're not using the ALU, you can turn it off and save some power. That's what the enable is for, is to turn it off when you don't need it. All right, so the next question. So now we kind of know, what component is doing all the processing. But then the next question is, well, after we do the adding, how do we get the result back to update register B? That becomes the second question. So the second question is answered by tracking this output here, because this is the sum of the adder. So the question is, how do we route the result of the addition all the way back to register B? Well, the first thing is, how do we get it out of the ALU first, right? So to get this out of the ALU, if we were to move it around a little bit, and I'm going to turn off my Discord because it's a little distracting. There we go. So we want to connect input 0 of the multiplexer to the only output. So that means, we need to use a select, and you probably guessed it right. It is the same select as the other select for the 2 demultiplexers. It's the same thing. So the input and the output, they're all synchronized, okay? And if you look at the enable, can you guess where the enable is going? It's the same enable as the 2 demultiplexers. Okay, so the 2 demultiplexers on one side and then the multiplexer on the other side, they're fully synchronized. Okay, in other words, they're simply routing, who is doing the processing. And then this is the output pin. So the output pin goes back out, out of the ALU. So now we can go back to the main circuit. Okay, are there any questions about this diagram, just for the purpose of understanding how do we control the routing inside the ALU to perform an addition? Okay, we're all good? Okay, so now we're going to go back up to main, which looks super messy. This is the output of the ALU. So now we need to track this thing and go like, how do we get this back to the register bank and update register B? So now we follow the thick line and go like, well, it ends with this particular multiplexer. So if it ends with a multiplexer and we needed to get into here, then the question is, how do we configure the multiplexer so that input 1 connects to the output, which then connects to the input of the register bank? Does that make sense? Because we want the wire that is currently highlighted to connect to this wire over here? And the answer to that question is one, we need to enable this multiplexer. And then the second thing is we want RI mux, which is register input multiplexer. I should have named it as register input multiplexer select, but that makes it even longer. So I just name it as RI mux. That needs to be what? You got two choices. You got a 0 or 1. So what should it be? 1. That's right, because we need to connect input 1 to the output, so the select needs to specify 1. Okay, so once we have that, we can now go back into the register bank, and then we ask, how do we update register? How do we update register B? Well, we track down the input of register B. It goes to the input pin. Okay, no big deal. That one we know already. Then we look at the clock. Well, it just goes to the global clock of everything. So no mystery there either. But the most important part is the enable, because the enable pin is the only one that is unique to each register. So we look at the enable pin of register B, and then we track it down to the decoder. The decoder is output 1 of the decoder, which means in order for this wire, the one that is highlighted, to be a 1, I need the enable of the decoder to be a 1, and I also need register input select to be 0, 1 in that case. Is that okay? So we have almost figured out everything except for the output of the register bank. So I need this thing here to be connected to register B. So I need register output 0 select to be 0, 1. I need this one to connect to register C. So that means I need register output 1 select to be 1, 0. So now I know every single configuration bit that I need inside the register bank. I know exactly what I need in the ALU. So what is remaining is the routing, okay, outside of the register bank and the ALU. Somehow I need to route this thing all the way to here, and then somehow I need to route this wire all the way to here. So it's really just a matter of, okay, so I need to go from here to here. The only thing in the way is a demultiplexer. So I need this particular demultiplexer to have a select of 0, 1, because it is corresponding to output 1. And I need to make sure that it is enabled. And then with the other one, which is, oh, where is it? There you go. This is where it is. So for this one, it's a little bit more complex because it has a demultiplexer and also multiplexer. So to configure this demultiplexer, well, let's deal with this one first, okay? So to deal with this multiplexer, I need input 0 to connect to the output. So that means the select of this multiplexer needs to be a 0. And I know it's not doing that right now, but we'll go ahead and try to figure out how to make it happen. And once we track it down to the demultiplexer, then we need to look at, oh, this is output 1 of this demultiplexer, which means this particular select needs to be a 1. So knowing all of that stuff, okay, now we know kind of how to configure it. Except for one thing, because FC is not something that we can directly control, because FC is calculated. FC is the NAND between register output 1 demux and the ALU enable. But to do any calculation, the ALU has to be enabled, which means this one is going to be a 1. And then this is register output 1 demultiplexer, which is corresponding to this Y over here. This demultiplexer also needs to be enabled in order to finish the routing. So that means we need to have this one as a 1, this one also as a 1. So FC is going to be a 0 as a result of that. So that means this particular multiplexer is going to get the right select regardless. Are we still doing okay so far? I know there's a lot of detail, but just but each step is not complicated. It's just a lot of tedious stuff going on. Are we doing okay so far with this? So the next question is, okay, the next question is the biggest question, is who gets to decide these things, like RI mux and RI cell, RIEN, register output 0 enable, register output 0 select, blah, blah, blah. Who gets to pull all those strings? So now you have to track down these guys, right? Just highlight one, and then you scroll down, and then you'll find they are all basically outputs of the ROM. So if you think about each control signal to each multiplexer as a time inside inside the music box, the drum with all the little things that protrudes, this is the mechanism. This is the drum of the music box. Is that okay? Does everybody understand the analogy, what I'm trying to say? Okay? So so that means the content of this ROM here is dictating what the processor or what the components of the processor should do. Who is connected to whom, who's doing what, they are all dictated by the content of this ROM component here. Is that okay? Let me just highlight the ROMs just so that we know which ROM we are talking about. There's only one ROM, by the way, but I do want to point it out. Is that okay? So this ROM, you can look at each location as, an instant of time. Okay, what notes is it playing at that particular instant of time? That's basically what each location of the ROM is specifying if we were to use the analogy of a music box. Is that okay? So in order to play a tune, you need to play, oh, okay, at this instant of time, I want to play these notes. In the next instant of time, we want to play some other notes and so on in order to play a tune. And that's what this adder is for, because this adder, combined with a microcode pointer, it can do the self-incrementing thing. So this way, it is possible for us to automatically advance to the next location, and then the next location, and then the next location. Is that okay so far? Okay? So if I want to add, then I'm looking for a certain ROM location that basically orchestrates the necessary connections to get it done. So this is where the opcode comes in handy. Okay, so let me show you, how do you choose which tune to play? Okay, so I'm going to show you the mechanism that controls which tune do we want to play. You can kind of look at this as a cross between the music box and the jukebox. Do we know what a jukebox is? No? Okay. Let me show you what a jukebox is, because I think this will help you guys remember and understand the concepts once you can associate it with something that's physical. So a jukebox is like this. It's basically a device. Okay, let me see if I can get a close-up on one of these. Oh, that's good enough. Let me click on this one and click on the image itself and just magnify. There we go. Nope, it doesn't like to magnify. Okay, that's okay. So if you look at the jukebox, the rest of it is kind of mostly just speakers and just making it look nice. Um, what it does have are buttons, so they allow you to select which music or which song you want to play. So it's fully automated. You walk up to it, you put like your money or token into this little slot here, and then you get to select which song you wanted to play. Um, so it's a selection mechanism, okay, of which song you wanted to play. So when I said, the combination of a music box and a jukebox, that means, you still have a selection mechanism here to select, oh, I want to play this tune. But the playing of the tune is the mechanism of a music box. Is that okay? All right? All right, so now we're going to switch back to Logisim, and I will explain, how RAM comes into this entire picture. Because if you look at, what you can use to specify the content of the microcode pointer, one way is the adder. So you can see how this adder here is feeding back to the microcode pointer. So this is useful because it gives you the ability to increment. Okay, so you can get to the next location and the next location and the next location, which means within the same tune, the music box has a mechanism to rotate the drum using the adder here, and as long as the multiplexer is choosing input 1 to feed to the microcode pointer, you are basically playing the same tune, the next note, the next note, and the next note of the same tune. But the question is, how do we get a tune to start? How do we choose a different tune? So that has to do with the other input, right? Because we have two inputs here. One input is just the increment of whatever it used to be before, so it's good for playing the next note or the next bar of a tune. This is the one. This one here, on the other hand, can specify an entirely different tune because this one has nothing to do with the auto increment mechanism. It has to do with something else. So now we have to track this one back and say, where is that coming from? So we track this one. It comes from a splitter, but one major portion of the splitter. This is also a very interesting splitter. I'll explain that later. But the major part of the splitter comes from a tunnel that is called instruction. Instruction as a tunnel is up here. I could have just wired the whole thing, but the use of tunnel means I don't have to cross the wires and make the diagram easier to read this way. So when you track down instruction, it is the output of a register. This is called the instruction register. And you look at this instruction register. Every time you look at a register, the first question that comes to your mind, there are two questions that should come to your mind. One is, where is the output of this register going to? The second one is, where's the input, right? How do we get something into the register? What does it mean? What is the meaning of this register in the grand scheme of things? So when you track down the input, which is this particular node here, then you go all the way up and go all the way across, and you see what is highlighted? It's coming from the D port of RAM. So that means there is a pathway between the RAM component and the instruction register. That is how you can play a new tune. That is how you can select which tune you want the processor to play, is by using the content of memory. Is that okay? Now, I haven't really explained here like the blow by blow, bit by bit, wire by wire explanation, but you see the connection, right? You see the possibility, the pathway of using the RAM content to update the instruction register, and then in return, the instruction register can be used to update the microcode pointer. The microcode pointer becomes the address of which location in ROM you want to access, and the location of ROM dictates how things are configured in the rest of the processor, like all the registers, the ALU and whatnot, and how the pathways are built between the components. Are we still doing okay so far? Okay, so right now we just need to focus on the kind of like the big picture, not so much on the details. Now, what does that have anything to do with the von Neumann architecture? What makes the von Neumann architecture the von Neumann architecture? We use memory to to specify the behavior of the computer, right? This gives us that capability. There's a pathway from RAM, which is memory, to the music box mechanism, so we can select which tune to play. That is the connection. Okay, this is why it is a von Neumann architecture. All right. So what we'll do next is to say, okay, fine, but show me how we're going to add the content of register C to register B, because I want to see that actually happening. Okay, so let's go ahead and explore that. And to do that, we have to go back to the shared folder, because there's one file that is particularly useful for what we are about to do. So if you go to the processor subfolder, there is a spreadsheet called opcode table. And I'm just abusing a spreadsheet as just a table. There's no actual code whatsoever. It really is just a table here. So this table has a few notations. When you see XX, as lowercase xx, it is trying to specify 2 bits to specify one of the 4 registers. If you want to specify register A, it's 00. If you want to specify register B, it's 01, and so on. Haven't we seen something like this related to something like this before? Inside the register bank, right? So inside the register bank, we have that decoder. Remember the decoder and also the multiplexers? So the select for the decoder and the multiplexers exactly just use these two bits, okay, to specify, are we talking about register A or B or C or D? That is how we designate which register. YY is the same thing. I have XX and YY simply because sometimes you need to specify two registers to complete one operation. Is that okay? So XXYY are really just a placeholder and say, hey, we got two bits over here to specify one of the four registers. Okay, that's all they mean. Um, so we'll ignore what I is representing right now or all the flags. So what we want to do now is to find out using column, well, either column C or D of which opcode here is going to correspond to what we want to do. All right, so let's take a look at column C. Column C is basically expressing the operation in a C++ notation. This is also called register transfer notation, or RTN. So if you go to a four-year university, you might need to know what is RTN. So I'm showing you this portion, and I want you guys to identify which row may be doing what we want to do. I'll give you guys like 20 seconds or so, to tell me which row may be the one that we're looking for, or it relates to what we want to do. Hmm? Row 24. So we got, yep, that is correct. So row 24 it is. Okay, so row 24 is specifying, how we can tell the processor to add a register to another register. Now, does it say specifically we're adding register B to register, excuse me, the other way around? Does it specify that we're adding register C to register B? No. It has placeholders. It's basically saying every time you want to add register Y to register X, this is the row to look into. So the next question is, what do we do with this row? Okay, now that we can identify this has to do with adding, because column D says what? Add. That's exactly what we want to do. Okay, but how do we make use of this row here? The first thing is you need to find out what two registers to use, which one is X and which one is Y. So when you look at the column B is known as the mnemonic. M-N-E-N, mnemonic. M-N-E-M-O-N-I-C. That's it, mnemonic. And for those of you who want to remember mnemonic, um, this is a, I'm getting distracted here. My brain is distracting itself. But there's a movie called John Mnemonic. There we go. And it has Keanu Reeves in it. Um, it's a it's a sci-fi from way back when. Okay, you guys probably remember Keanu Reeves in The Matrix or um, John Wick. This is like way back then. Okay, this is way back when he's much younger. It's an interesting sci-fi show. Basically they turn the human brain into a hard drive for smuggling data, and that's what the main character in the show is trying to do, is to smuggle data to the rebels. Um, Interesting, science fiction, and of course, it has Keanu Reeves in it, and I would say he fits that role really well. There are only two things you can say about Keanu Reeves in a movie: he's playing himself, or he's not. This is one of those when he's actually playing himself. So it's a good movie. Anyhow, um, so this row B is called a mnemonic, which means it is a crude attempt to make it easy for us to remember how to specify an instruction. Now, this one is not bad, okay? Add, well, I mean, that kind of spells out what it's supposed to do, right? But then you have something that is not so obvious. I'll give you one. CMP. CMP is compare. And then we have ST. What is ST, right? Store. and the LD is load, and so on. You can actually see the description on in column D. But this is called a mnemonic because back in those days, people do not want to spell or use characters unnecessarily. Can someone kind of guess why, why we want to make everything so short, to abbreviate to the point where it's like, well, I mean, it's hard to remember because there's CPR, which is compare, copy register, and then there's CMP for compare. Okay, so why do we want to make these mnemonic as short as possible instead of spelling it out?
To save space?
To save space, or I should say to save paper. What do you mean by paper? Who writes stuff on paper? What does that have anything to do with computer? Okay, so traveling in time. Okay, imagine this is I hate to say it, but the magic school bus, and we're traveling back in time. Okay, and I'm the teacher, obviously. So we're traveling back in time, back into the late 50s and the early 60s. Okay, so how do people store data back in those days? Flash drive, SD card, or maybe floppy disks, right? I mean, has to be floppy disk. Nope, punch cards. Punch cards. And punch cards do not punch themselves. If you want to write a program using punch cards, guess what? You are the one who's going to be punching the card. So that is why we want to make the mnemonics as short as possible because you don't want to punch unnecessarily because it's a painful process. The more you have to punch, the more chances you have to make a mistake. So it's not a good thing to basically make the mnemonic as long as it is. It's to spell it out. There's no spell check when you're punching punch cards. I mean, I'm sorry, but there's just no spell check in that case. There's no autocorrect. There's no syntax highlighting. There's nothing. It literally is just you, the paper cards, and the puncher.
There's a picture that went around a while ago where the code the programmer was standing next to the stack of paper
Yep.
containing all the code of the
Yep.
Fallout 13 machines.
And the interesting thing is, at a later point, the punch cards are sequenced. So if you so happen to kind of knock down a stack of punch cards and you lose ordering, there's a machine to reorder the punch cards to the right order.
Oh, I was gonna say, like, man, that'd be a nightmare.
Yes, it was a nightmare before the auto sequencing. Yes.
Like,
There's a reason why they built in the auto sequencing thing into the punch cards.
I have trouble keeping track of my code once it gets like really long. Like I wouldn't imagine like knocking over a step.
Yep. Well, this is okay. So what you said is interesting because it relates to what I want to tell you guys about writing a program in C and C++ and all the high level programming languages. Always make your function fit in one page of your editor. So this way, the entire thing is displayed in its entirety. You don't have to page up 4 times to get to the beginning of a function, and then page down 4 times to get to the end. And then one of the branches is going to span over 2 pages. That would be bad. That would be very hard to debug. But if everything fits in one page on your screen in the editor, it makes it so much easier to say, oh, okay, so this is the else branch of that condition, and then this is the loop, this is the conditional statement inside the loop, and so on. So that's just my experience of having been burned by subroutines that are way too long and have to debug those things. All right, so getting back here, okay. So column B is known as the mnemonic, which is a way to specify an instruction. Column C is called the RTN, the register transfer notation. Register is really just an explanation using English words. And what about column A? What about column A? Column A looks really not so friendly. I mean, the mnemonic is semi-friendly, okay? We'll say semi-friendly in quotes. But column A looks absolutely unfriendly because it's just a bit pattern. Dang it. So in this case, it is a bit pattern of 1, 0, 0, 0, and then X, X, Y, Y. I mean, what X, Y are we talking about? Remember earlier I said XX is the placeholder to specify a register. YY is the placeholder to specify a register, right? So XXYY relates to, guess what? X and Y. So now the question is, which one is our X and which one is our Y? What do you think? So let me go back to the text description of what we are trying to do. This is what we're trying to do. And let me turn off the line number because that is actually interfering with what we want to do. So this is the same thing as b equals to b plus c. So who is x and who's y? I mean, just do a pattern matching thing, right? X is the one that is supplying one of the numbers to be added, but that's also the one being, storing the result. So X is B in this case, Y is C in this case. Well, if that is the case, what is XX and what is YY? Remember, there's a little, okay, I'll go back to that line just to be sure. There we go. So we have this thing here. So if we already know that XX is register B, so what is the bit pattern for XX? 0, 1, and then YY is going to be 1, 0. Okay, so this is how we figure out those two bits. So we know XX is 0, 1. We know YY is 1, 1 in base 2. So now we get back to row 24, and now we can construct the entire opcode. Okay, so column A is corresponding to opcode. Opcode stands for, guess what? Operation code. That's it, okay? There's no magic to it. It's just operation code. But it's in binary. It is not friendly. It's not human friendly. It's hard for us to remember those things. So now we're going to construct the actual opcode. So the part that is all spelled out without the XXYY, that you have to copy verbatim, which means we have 1, 0, 0, 0 that has to be there. And then the XX is a 0, 1, and then the YY is 1, 1. So now we have an opcode. Yep. Uh, that is correct. It's supposed to be 1, 0, not 1, 1. Thank you. I just made a mistake. There we go. Very good. All right, so what do we do with this opcode? Okay, the first thing we do is we look at this and go like, let's convert it into hexadecimal. So if we are to convert 10000110 into a hexadecimal number, what would that look like? So it's a table lookup thing, right? You look up 1000, and then you match that to the hexadecimal digit, which is okay, 1248. We don't have any 1, 2, or 4, but there's an 8. So that's just 8, right? So this is 8. And then we have 1, 2, 4, 8 again. We have 1, 2, we have 1, 4. 2 plus 4 is 6. Okay? So this time we are not using A, B, C, D, E, F, because all the values are less than or equal to 9. Okay? So now we say, okay, so in hexadecimal, this is 8, 6. All right, then what do? We put it into RAM. Okay? Remember, in the von Neumann architecture, RAM specifies what we want the computer to do. The opcode goes into RAM so that we can now tell the processor, hey, we want to add register C to register B. Go do it now. Is that okay? All right. So now we switch back to Logisim, and I'm just going to hard code it. Okay, so I'm just going to go to this location and say, let's change this location to, what was it again? 86, right? So there we go. So now we have a program with only one single opcode, and we're going to execute it. We do okay so far? Okay? And the result of this execution should end up with register B being the sum of what register B and C used to be. Register C gets to retain its value, but register B is going to be changed. Are we good so far? All right. So this is when you might want to jot down the time, because you might need to get back to this part from time to time, because I'm going to explain the processor cycles, in this part of the discussion. So it's about 10 o'clock right now, okay? All right. So now, how do we track the execution of this instruction? The first thing you want to do is to start with the music box mechanism. This is the music box mechanism. Now, when you reset everything, when the processor wakes up from power up, it always starts with location 000 in ROM, because all registers reset to, guess what? 0. Okay, so the micropole pointer, just like any other register, has this reset line connected to a global reset that resets it to 0. I'll explain why there's an OR gate here, but later, okay? So now we look at this location here, location 0, 0, 0 of the ROM, and it looks like a big mess, okay? Because those are all hexadecimal digits. So you can always convert it back into the individual bits, but you can always just look at the output here and find out what the individual bits are. So the next thing you need to do is to track down, what does that mean? What does this 1080007 mean? In other words, where are these bits all going, and what are we really doing with this particular cycle of the instruction? So this is where it takes a little bit of practice, okay? But there are only a few things you need to look first, okay, to determine what is being used. My first one is always RAM. In other words, you want to see if RAM is being used with location 000. So this is what RAM looks like at this point. So can someone tell me, am I about to use RAM? And if so, what am I doing with it? In other words, am I reading or am I writing to it? How do we know? First question first. Are we using RAM? Is RAM being utilized right now? How do we know? Is it being selected? In other words, if RAM is not being selected, we know for sure that whatever we are about to do does not involve the RAM. But in this case, yeah, it looks like we're going to involve the RAM because the RAM is selected. Okay, so that answers the first question. So once you confirm RAM is being used, now you got a bunch of questions to ask. The next question is, are we reading from RAM or are we writing to RAM? How do we know? The LD, exactly. So LD is a 1 right now. And by the way, RAM load is just a fancy name of one of the bits coming out of the ROM. Okay? Because I'm just spelling out what that particular bit is trying to specify. It specifies the load port of RAM. Okay, so if load is a 1, what are we doing? Are we reading or writing? Well, you can always hover over the port, and it kind of tells you the answer too. So it says, if 1, load memory to output, which means we have a read operation. All right, so now we have answered 2 questions. We are indeed using RAM, and we are reading from RAM. So what do you think would be the 2 natural questions to ask? Right, exactly. So the input in this case is what location are we accessing? And then the second question is what is the output? But we are not just asking what is the input and what is the output. We're more asking who specifies the input and who is going to use the output. Is that okay? So once again, we are tracking down the dependency between the components, and we're asking questions that are kind of intrinsic to what the component does. Okay, so first thing first, we want to find out who is specifying location 0, 0 in this case. So now we track down the A port. The A port goes all the way to a multiplexer. This multiplexer is, which input is it selecting to connect to the output? Can you see visually which input is being used? Yes, you can. Because when a wire is 1 bit wide, if it's light green, it is a 1. When it's dark green, it is a 0. So this one you can actually visually tell. It is a 1. Okay, the select here is a 1, which means input 1 connects to the output for this multiplexer. Okay, so what do? We track that one down. Okay, so we track this one down and go like, okay, let's find out where it goes. It goes to the output pin here for debugging purposes, so you can ignore that for now. But it comes out from the PC. Okay, the PC is called the program counter. Now the program counter is super duper important, despite the name does not imply so, because this contains the address of where we are getting the opcode. All right? So by changing the program counter, if we increment, we are moving on to the next instruction, but there are jump instructions that allow you to change the program counter in a dramatic way so it can alter the path of execution. Are we still doing okay so far? All right. So, okay, so this is good, okay, because this means, the program counter is being used to specify which location of RAM is being read, okay? So now we managed to answer a few questions, but there's one more question that we have not answered yet, is where is the data output of RAM going to? Who's utilizing the content, right? So now we need to follow up with that question and try to answer the question. So now we go all the way back to the RAM component, highlight the D port or the output wire of the D port, and this one goes everywhere within the processor. So now you got a few things you need to figure out is, okay, fine, which one is being used in this case? So you can see how it is going into this multiplexer and going into the register bank, but I know the register bank is not utilizing what is on the data, what's on the data line. How do we know? This multiplexer here, is it enabled or disabled? Can you visually tell whether the multiplexer feeding into the input of the register bank, is it enabled or not? How can we visually tell? The enable, right? Is it enabled or not enabled? It is not enabled. Very good. Okay, so you can see this is the enable of the multiplexer, and this is dark green, which means the input to the register bank is not enabled. So that means I don't even have to bother to figure out what's going on inside the register bank at this point because it's not enabled. So now we track down the other route, which is going to this multiplexer. And what about this multiplexer here? Do I have to be concerned about this multiplexer? Nope. Because it has a select of dark green, which is 0, and the wire that we have highlighted is input 1. So the output of this multiplexer is not using the output, the data of the RAM component. So that's also a dead end. Okay, fine. What else? Well, it kind of branched out over here. We look at the demultiplexer here. And the demultiplexer is also disabled, which means that is not a concern of ours either. So now we have to scroll down, okay, to track down this side of the node, and it goes into the instruction register. So that means the instruction register is already seeing the content of location 0 of RAM. Is that okay? Can we confirm that? Well, let's see. So we can click on the wire, and it shows that it has 10000110. Isn't that the output that we just figured out? Yes? Okay. So now, the next thing we will do is to have a clock, is to exercise the clock. So we go to the clock pin. Okay, so when you're tracking things like this, it's really difficult to track down the clock pin and click it. So one other way to to give it another edge is to use tick once, which is Control T. So on the keyboard, you can type Control T, and then the clock line, which is this one here, will transition to the next state, which is, in this case, it's going to transition from 0 to 1. Are we doing okay so far? Okay. Can someone remind me again, usually what happens when an enabled register is seeing the clock transitioning from 0 to 1? It'll update, exactly. So that means when I type Control T right now, I'm expecting the instruction register content to update to exactly 86 in hexadecimal. So here we go. I type Control T on the keyboard, like so. Aha, okay, so the instruction register is now updated. So the falling edge usually doesn't do anything except for one single register. Okay, there's one register that is sensitive to the falling edge of the clock. And you probably want to kind of do this exercise a few times so that you remember that. This register here, the microcode pointer, is the only register of the entire processor that is sensitive to a falling edge. Everybody else updates on the rising edge. The microcode pointer updates on the falling edge. How do we know? Right here. Okay, so when you select this register, it will tell you that the trigger is a falling edge and not a rising edge. Everybody else has a rising edge except for this one. Is that okay? Okay, wait, hold on a second here. So that means if I change the state of the clock again, which is going to be a falling edge, the microcode pointer is going to update, right? So if you are doing this exercise on your own, what are you going to do? Are you just going to type Control T on the keyboard and see how it's updated? Or are you going to try to figure this out first, and then you type Control T to confirm that your understanding is correct? I will leave that up to you, okay? This is a question that only you can answer. But if it's me, I'm going to try to figure this out first, predict what's going to happen, and then Control T and confirm whether my understanding is correct or not. All right? So now I have to look at the microcode pointer. I know it's going to update because it is always enabled. Okay, the enable is a constant of 1, and I'm going to cause a falling edge. And according to this part here, this register does update on the falling edge. So the question is, how is it going to update? What is the next value of this register? So now I have to track down the input to the microcode pointer. It's coming out of a multiplexer, so that means I have to track down which input connects to the output for this multiplexer. The select is a 1, which means input 1 connects to the output for this multiplexer at this instant of time. So now I need to track down this wire, which is coming out of the adder, right? This is the adder, which is just adding 1 to whatever the microcode pointer has. So that means when I click Control T, the microcode pointer will increment to 1. Is that okay? Which also means the ROM would end up highlighting, location 001, which also means the output of this ROM, the D port, is going to reflect the bit pattern specified by location 001. Is that okay? Is that okay? This is how we control the behavior of the processor. In this case, I'm just playing that tune, the next note of the tune. We're just incrementing in this case. All right, so let's do a Control T. This is called the fetch cycle, by the way. Okay, so what I have just described up to this point is called the opcode fetch cycle. This is the cycle where we go to the RAM pointed to by the program counter and grab whatever is at the address location and put it in the instruction register. That is called the fetch cycle. Are we good? Okay. So now what do we do? Well, let's go ahead and do this falling edge, and we can see how the microcode pointer is indeed incremented to 1, and now we are at a different location, which specifies a different bit pattern. So once again, we have to figure out what is the processor doing, okay? What are the components doing in the processor? So once again, we're gonna go to the RAM component and see if the RAM component is used. Because if the RAM component is used, it will automatically prompt a bunch of questions. And in this case, we can see the RAM component is not being used because it is not being selected. You go like, okay, so we don't have, that saves us a bunch of questions, right? But it opens up a bunch of other questions. It's like, if RAM is not being used, who else is being used? So this is where you want to track down the enable of the registers, okay? Because a register needs to be enabled in order for the rising edge to update it, right? So if the enable line is disabled for a particular register, the rising edge doesn't mean a single thing. Is that okay? So now we look at the various registers and see if they are enabled. So you can do it in a more systematic way, but there are only very few registers floating around in the processor. And I advise you to basically download this whole thing, turn it into a PDF, and use color coding, okay? So you can highlight all the important components so you don't get lost easily when you're trying to figure out what an instruction does. So I can point out to you right away, the program counter does have an enable of 1. In other words, the program counter itself is going to be updated when we have a rising edge. Okay, we are right at the cusp of a rising edge because the clock is already a 0. So the moment I type Control T, it's going to update to a 1. So now the question is, how are we updating the program counter? Okay, so I know I'm spewing out a lot of details, but what you really need to focus on is the method, is the way that I ask those questions. Okay, if I know something is going to be updated, I automatically ask the question of how is it going to be updated? Who is supplying the data to update this thing with? Okay, so those are the things that are super duper important because I'm just looking at the dependency between the components and ask the questions accordingly. All right, well, let's figure it out. So the input of the program counter connects to the multiplexer. So I need to now find out which way the multiplexer is connecting the inputs to the output. We can see this is a dark green, which means it is using input 0. And the reason why it is dark green is because PC mux is dark green, and we'll figure out what is PC mux in just a little bit. So input 0 is connecting to the adder, and the adder is simply adding whatever the program counter has. It will just increment it to the next available value. So that means on the rising edge, the program counter will update to 1, 0, 1 to be exact in hexadecimal. It moves on to the next location. Is that okay? Why? Because we have already fetched the opcode of location 0. There's no need for me to stay there anymore, right? The program counter says, I need to update to the next available location. So if the program has multiple instructions, now I'm ready to fetch the next instruction in the next cycle. Yep.
I know you showed this earlier, but what exactly specifies like the address of the ROM of the PC?
Are you referring to PCMux, how we compute PCMux, or are you referring to the microcode pointer? Because the microcode pointer is the only thing that dictates where we are in the ROM. Yep. Okay. So right now the microcode pointer is static, and we are about to update the program counter. But the earlier question was, who is PCMux? So PCMux turns out not to be something that is directly coming out of ROM. It is actually computed up here. So PCMux is corresponding to this tunnel over here, which is which is the result, the output of a multiplexer. The multiplexer takes a bunch of inputs, but if you look at the actual select PCMux mux, okay, because this is the multiplexer that determines the output, that determines the behavior of another multiplexer. So it is 101. So if you look at 101, it is 5. So when we look at input 5, this is input 5 here, it is a 0. That's why PCMux is a 0, because PCMux, which does come from the ROM, is saying, okay, choose input 5 of the multiplexer to be the output, which turns out to be PCMux, which is in return is used to determine what input do we use to update the program counter. Is that okay so far? So the net result of all of this is the program counter is going to update, and it's just going to increment. Okay, so we are ready to do that now. So let's do a Control T, and voila. So this particular step has no name. Okay, the previous one is called the fetch cycle. This one is just auto-incrementing the program counter and has no particular name to this particular one. Okay, the next one is interesting. Okay, because what do we have now? Are we going to have a falling edge or a rising edge? We're going to have a falling edge. Okay, there's only one thing you need to look when we have a falling edge, and that's the microcode pointer, because everybody else does not care about falling edges. Okay, so now we go down to the microcode pointer, and then we ask, okay, how are you going to update this time? Once again, we look at the D port, and it's coming out of the multiplexer, but this time the multiplexer has a select of 0, which means we're going to use this wire to update the microcode pointer. It's not incrementing anymore. So if it's not incrementing anymore, how is it going to get the value to update? Why are we looking at this pattern here? 1 0 0 0 0 1 1 0 0 0 0 0. Wait, hold on a second here. That does resemble a little bit of the opcode that we just determined earlier for the add instruction. except there are 4 more zeros on the right-hand side, right? Look at this part here. That's the opcode that we worked out earlier. And somehow we ended up with 4 extra zeros as the least significant bits. How did that happen? What do you think? It has to do with the splitter. The splitter is responsible for this. So the splitter here is saying the instruction node, which is the output of the instruction register, is going to supply bit 4 to bit 11. This is bit 4, bit 5, bit 6, 7, excuse me, yeah, 7, 8, 9, 10, 11. Okay? Then who's supplying the zeros? Bit 0 to bit 3 comes from a constant of 0. That's why it has the 4 least significant zeros, and then the most significant 8 bits are really just the content of the instruction register. Is that okay? Because this is really, really important of how the instruction register is used to update the microcode pointer. Are we doing okay so far? All right. So that means on the falling edge, the microcode pointer is going to update to 860 in hexadecimal. Does that make sense? Because we are right at the cusp of a falling edge. If I control T just one more time, it's going to be updating the microcode pointer. All right, so let's do that. Okay, so control T, there we go. And now you can see how the ROM is going to location 860. This particular step that I just performed also has a special name. It is called the decode of an opcode. Okay, decode, which means let me look at that 86 instruction and figure out what I'm supposed to do with it. This is the decode cycle of an instruction execution. And you can see this particular bit pattern here is not like the other two that we have seen before. In other words, we are now playing a different tune. Okay, in the jukebox, we have just pressed a button, and now it's spinning up the drum of another tune. All right, so now we need to go through all that exercise again to figure out what it's trying to do. So the light green wires are always useful to us. So you can see how in this case, IN, EN is enabled. So that means one register is going to be updated in the register bank. Does that make sense? Because inside the processor and inside the register bank, you can also see this decoder is finally enabled. Register B is about to be updated, right? And on the outside, we also want to see who else is active at this point. You look at the ALU, you can see the ALU enable is also a 1. So that means, oh, so we are going to update one of the registers. The ALU is going to be active. So when the ALU is active, you want to find out, okay, what are we doing with the ALU? So once you go inside, you can see the instruction or the operation that we have selected is 000, which means we're adding. The ALU is enabled, which means this input goes to the first input of the adder. This input here goes to the second input of the adder. And then the output of the adder is going to go through this multiplexer, which is also enabled at this point, and it's going to go to the output pin. Is that okay? So now we go back to main, and then we ask, what are we using to feed to the 2 inputs of the ALU? That would be the next question. So we track down in 1. It comes out of the demultiplexer here. The demultiplexer is enabled, and the select here is specifying 0, 1. So that means the input connects to output 1, which is exactly what we want it to be, because we know in 1 of the ALU is being utilized. So we know one output 0 of the ALU now connects to in 1 of the ALU. What about in 2? Well, if you look at in 2, it comes from a multiplexer. The multiplexer has a select of dark green, which is 0. So input 0 is coming out of a demultiplexer, which has a select of 1, which is okay, because that's exactly what we want, because we want this particular node to connect to something useful, which is the output 1 of the ALU. All right? So at this point, we know the 2 outputs of the register bank are utilized to feed to in1 and in2 of the ALU, the ALU is indeed enabled, and we are specifying an add operation. So the remaining question is, what are we doing to the output of the ALU? So let's go ahead and track that down. So the output of the ALU, which is here, is going all the way back to a multiplexer. So this multiplexer has two inputs, but according to the select, which is RI mux, which is a 1, we are indeed feeding input 1 to the output, and it is enabled, right? So that means the result of the adding is indeed going back into the register bank. The question is, who is going to be updated for this particular operation? So once again, we get back into the register bank, and then we use the decoder. The decoder is now turned on, and we are using 0, 1 to select which register is going to be updated, and that is indeed register B. So that completes the entire cycle, okay? Because now we have tracked down all the bits, all the components to see that, oh, so this is doing what we wanted to do earlier, which is to feed register B to one of the inputs of the ALU, feed register C to the other input of the ALU, use the output of the ALU to turn around to update register B. That is exactly what we're doing now. Now, the thing about using LogicSim is you can always double check. Okay, you can click on the wire and see what it is. So it is saying that the input is for, let's see, this is for D, because 1100 is a C, so we are going to update register B to 4D. Would that be the correct thing to do? Is 4D 4B plus 2? It is, okay? So when we do a rising edge, you can see that is exactly what it is accomplishing. So you might think, oh, Tag, this is good. This is the end of the lecture. No, there's one more thing. There's one more thing, which is, what do we do after this point, okay? So what do we do after this point? It's going to be a falling edge, and we know a falling edge only affects the microcode pointer. And according to this, the microcode pointer has the multiplexer feeding the microcode pointer has a select of 1, which means we are only incrementing the microcode pointer to 861, right? So let's do it, okay? Control T, you go like, whoa, what just happened? It's supposed to be 861, and how come it is 000 right now? Exactly, because the location 861 contains a bit pattern that resets the microcode pointer back to location 000, so we can start the fetching of the next opcode. So that concludes the entire performance of the processor to execute a very simple instruction to add 2 registers and then put the sum back into the first register. Is that okay? I know it is tedious. I know there's a lot of stuff going on, but are you making the connections, the logical connections between the steps? I'm not asking anyone to memorize this whole thing, okay? Because the exam is always going to be open book and open notes. The question is, if given enough time, can you reason out the entire thing? Hopefully, right? Okay, so I'm going to release the lab today. I think it might be released already, just not the password. Let me go check. Alrighty. All right, so this is your new lab, and let me get back to see if it's already released. I think it is already released. I just need to give you the access code. Shingles, that's right. And the reason why it is shingles is because I think a day prior to that, I was getting the vaccination, not vaccination, but the, I guess you can call it vaccination of shingles. Because I have had chicken pox before, and getting shingles is quote unquote just a matter of time. So I'll write down shingles on the whiteboard so you guys can remember that. There we go. All right. So you will need to use Logisim for this particular lab. If you're having difficulty accessing Logisim because there's no Java on these computers, let me know ahead of time because I can give you some alternate. Alrighty. If there are no questions, I'm going to turn off the recorder and upload.